If you will recall, our job in chapter 12 is to look at functions of 2 variables, and then eventually functions of 3 variables, and then eventually equations in 3 variables, and eventually equations in more variables. What we're doing in chapter 12 is getting out of R2 and taking a few steps into R3. Going back and starting with describing functions in R3, so that we can go on to equations in R3 and then other things in R3. All right, we started with linear functions, nice simple stuff. We went back to lines in R2, y equals mx plus b, and we want to adapt that to thinking about describing planes in R3. Linear functions describe lines in R2 and describe planes in R3. Remember, we had multiple forms of linear functions. I should say forms of linear equations, because standard form is an equation, not so much a function. In R2, we had names for them. We had slope-intercept, y equals b plus mx. We had point slope, y equals y naught plus m times x minus x naught. And we had a standard form. ax plus by equals c. These are all descriptions that we use in our for lines in R2. These are linear equations, so they've got an x term and a y term, and both those are degree 1. No terms are the degree is all 1. There's no x, y, so like there's no degree 2 terms, all degree 1 terms. No weird stuff with like fractions for exponents, just power of 1. We get the same thing. We have the same kind of forms if we describe planes in R3. We just have more variables. So our slope-intercept we could say z is equal to z naught plus mx plus ny. We just extend this with extra terms. If instead of our points, the point that we know about being 0, 0, and then z naught, we could say that z is equal to z naught, start there, increase by m whenever x increases by 1, and increase by n whenever y increases by 1. These equations are doing the same thing that our linear equations did in R2. Start at this point and go in a direction. It's just that when we have a plane, we start at a point and we go in a direction in the x and a different direction in the y. We have a slope in the x direction and a slope in the y direction. So we have 2 slopes. We're describing 2 slopes. We know this is going to be making a plane because if I have a way to point in the x direction and a way to point in the y direction, I've got 2 different directions. If I can connect those up with one plane. 2 lines describe a plane. That's all we're using here. Even better, M and N describe slope in the same way they did in R2. M is the change in Z with respect to X, and N is the change in Z with respect to Y. Once we write things down like this, since we become aware of the fact that we're in a calculus class, and I just wrote dz dx, or delta z over delta x and delta z over delta y, and then we start thinking in terms of calculus. This is when we have two distinct points. What happens when we want to pull that back into one point? To find, for example, the slope of a line tangent to a curve at a given point. We need 2 points to make a line. How do we figure out what's going on with 1 point? If I just use 1 point, delta z and delta x are both going to be 0, and 0 over 0 is indeterminate. We'll figure out what is 0 over 0 in this case. Is it 0? Is it some constant? Is it infinite? So you can see the calculus start to show up, even though we're just describing linear functions. We also have a standard form for linear equations in R3, that is with 3 variables. We'll just have AX plus BY plus CZ is equal to, well, let's just call it D. Whereas our 2 function forms have like real tangible information in them, it doesn't look like we get a lot out of our standard form. What are A, B, and C, and D? What do they tell us with respect to the function, or with respect to our plane or line? So that's one of the things that we want to look at today. What do the coefficients in standard form tell us about the plane? That's one of the questions I want to think about today. Yeah. Yes. The question is going to be, how are they telling us directly? Right? The coefficients, that's a perfect observation. The constants tell us a place to start. The coefficients tell us how the x's and y's jump into things. That's going to be telling us what direction to go. Right? The reason that we can get away with just using 1 number for all this direction business, or 2 numbers for direction, is because lines and planes are very simple. Start here, go that way. And planes is like, I'll start here, angle it that way in the x direction, and that way in the y direction. So yeah, exactly. They're going to tell us about the direction, but we want to know, how do they tell us about direction? So let's think about it. We are going to do the same thing that we always do in this class. We want to know what's going on in 3 variables. Let's drop it down to 2 variables and think about that. So let's drop it down to 2 variables and think about that. Let's write an equation. Standard technique in math. Just use like add 0, multiply by 1, cut some stuff out of your problem. I'm going to write, let's say y is equal to, let's just go with 1 plus 2 over 3x. The 1 is not really important. What we care about is the 2/3 x. So in this, we see a change in y of a change in x. So our change in y is going to be 2. Our change in x is going to be 3. So this is normally known as the run. And our change in y is normally known as the rise. So I'm going to do a 2 rise and a 3 run. There's a line with a 2 rise and a 3 run. Let's write this equation in standard form. So I'm going to multiply everything by 3. Now I'm going to put the x over on the other side. So I get minus 2x plus 3y is equal to 3. See, we had a plus 2 rise. Plus 3 rise. So when we write things in standard form, since our slope was a rise over run, and we want to clear out the fractions, the first thing that happens, we notice that the run gets attached to the y, and the rise gets attached to the x. Everybody see that? Our rise is 2. That's on the coefficient of the x. Our run is 3. That's on the coefficient of y. Ain't that seem backwards? That seems weird. Also, our rise is a negative 2 coefficient. That ended up being a negative 2 coefficient, a positive 3 coefficient on the y. But we do see that that's how things got reorganized. That's what's going to happen when we multiply everything by the rise. It's going to cancel the denominator from the slope and put the run as a coefficient of y. And the rise yeah. That's what the coefficients are telling us, but it's better to think about that. So in terms of rise and run, it works better if we think about the slope. Slope of 2/3 as delta y over delta x up to right 3, plus 2 over plus 3. Or we could also go down 2 and left 3, because I could do a negative 2 over negative 3 and still have a positive 2/3. So that's still thinking in terms of slope. So as long as we're thinking in terms of slope, rise over run, that's how we want to think about it. But when we rearrange into standard form, the number that I've associated with the rise, the vertical change, is now in front of the x and it has the wrong sign. And the number I've associated with the run is now a coefficient of y. This is because we have to read the standard form differently. So first we want to notice that we're reading the coefficients in the standard form differently. Here's how we can read them. What is the slope of the line perpendicular to this line with a slope of 2/3? What is the perpendicular slope? So if a slope is 2/3, what's the perpendicular slope? Opposite and reciprocal, right? Perpendicular slope is the opposite reciprocal or reciprocal of the opposite. Let's draw that on our picture. A slope of -3/2 would drop down 3. Oh, sure, pick the one in the middle, so I have to guess where the points are. If you had a professional teacher, this kind of stuff wouldn't happen, but y'all are stuck with me. I choose to blame you. That's true. Now, if I had something to say about it, you would be, because you'd be like literally getting paid for doing this. So our slope is -3/2. Now let's break this into a rise and a run. Our perpendicular rise I can read as a +3. And our perpendicular run, I spelled X wrong. Notice that in our perpendicular rise and run, my perpendicular rise, my delta y, is a +3, the coefficient of y. My perpendicular run, -2, is the coefficient of x. What the coefficients are telling us in standard form are the directions of what's perpendicular to the line that the equation describes. The coefficients in standard form are saying the direction of what's perpendicular. So the coefficients of standard form, we look at the -2 in the x and the 3 and 3 coefficient of y, and say this line is everything what's perpendicular to a rise of 3 and a run of -2. The coefficients in standard form are describing a direction perpendicular to the line. The coefficients in the standard form are describing a direction that's perpendicular to the line. So when we look at those coefficients, we're kind of describing this equation is a line where everything is perpendicular to this direction. -2 in the x, +3 in the y. many of you been through linear algebra? Anybody been through? How many have been through physics 1? How many of you can already see that I'm going to be talking about vectors pretty soon? How many of you realize that this is normal? Get it? Normal. If you don't get that it's normal, that's another word for perpendicular. What we're describing with the coefficients in standard form is the vector that's normal to the line. So we're going to imagine an arrow. I realize I haven't described vectors. And some of you that read ahead in the book said, go, dude, vectors don't show up till chapter 13. You barely talked about chapter 12. And I'm like, oh, yeah, pretty much. And I go, isn't that unfair? I don't know. It just came up this way. We're describing the normal vector. The normal vector, or the coefficients in standard form, are describing the normal vector. We have lots of different ways of describing vectors. We just need to say what's the x coordinate, what's the y, or x component, what's the y component. We're just listing two things. We have lots of ways to list them. The coefficients in standard form describe a direction that's perpendicular to the line. They describe the normal vector. Now we want to expand this to R3. So when we look at this equation, ax plus by plus cz equals d. I spent too much time in R2, so I forget to write z a lot. The coefficients a, b, and c are describing a vector that is perpendicular to everything in the plane. That's how we can describe a whole plane with just one direction. Instead of describing the plane as everything that's a combination of these two lines, since we're in R3, we can describe a plane by saying everything perpendicular to this one line. So the plane is all the points, so the plane is perpendicular to the normal vector A, B, C. We had to abandon rise and run because we've got three different directions. There's a delta X, delta Y, and a delta Z. So rise and run right out. Since we've got two directions, a direction in the X and a direction in the Y, we can't summarize with just one number like we could with slope. How restricted things are in R2. So we just have another way of describing this plane. A plane can be described as everything you can make with these two vectors or everything perpendicular to this one vector. And that's what we're describing here. We have this vector, normal vector, A, B, C. And the plane is everything perpendicular. Yeah. In R4, if we just pick one vector, right? So are you imagining just one perpendicular to one vector? So if you imagine one vector in R4, that's using up one, and now we've just got three left. So instead of just one plane perpendicular, right? Because I've used up one in R3, back to R3. I've used up one to make my normal vector. I've got two left. I've got a plane. In R4, if I pick one vector, I'm going to have a three-dimensional space that's perpendicular to that one vector. Well, when we're describing things perpendicular, we have to get rid of things like time, because what's perpendicular to time is kind of weird, right? And besides, what we're trying to do is describe a four-dimensional space where it's meters, 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 and meters. Right? Is it hard to picture? Correct. It is hard to picture because we can't. We're programmed to think in three dimensions, and it's really hard to imagine where that fourth dimension goes. Right? Because it's easy to see the three. I've got left and right. I didn't realize I did it backwards. Left and right. I've got forwards and backwards. I've got up and down. Where's the fourth one go? Dang it! Nowhere to put it. It's hard to think about, right? It's hard to think about. Where do we put that fourth one? If I'm going to draw, we do have techniques for dealing with this, right? So I might call here's one axis. Here's another axis. Now the paper is done. Paper's like, oh, what are you going to do now? And we tell the paper, we're going to use our imagination. And we're going to draw this one. And the paper's like, oh, dude, what are you doing? That's in the plane of Y and Z. Because the paper is only thinking in two, the paper's not thinking. I have sedated the paper, so it's not thinking, don't worry. It's because the paper's ticklish, and so when I write on it, it starts laughing. It's really distracting. So the paper is thinking, this x-axis that you drew, that's just sitting in the plane, YZ plane. So I don't know what you think that is. But in our minds, we picture it coming out of the paper. Do you picture it coming out of the paper? Do you see? So you see that x-axis coming out of the paper, or do you see the x-axis going into the paper? I don't. One of those things. I don't have a 3D pen where I could just draw this coming out here and then do some like Minority Report stuff where I just like move my hands around and we like look at things from different angles and I like throw them over here. Oh, it's not a Minority Report thing anymore. It's a Tony Stark thing. So I can't like do a Tony Stark thing where I've got this hologram. I'll just go like this. I gotta wonder, did Robert Downey Jr. feel ridiculous when he was doing all that? Because he didn't see all the stuff in front of him. He was just like, that's true. They all had to do kind of crazy things, right? Like Doctor Strange had to spend some time like, oh. Anyway, so we can imagine this x-axis coming out of the paper. Now, let's draw a fourth. All we need is a fourth axis that's perpendicular to these three. Well, crap. I can draw one in, right? I can draw one in. And you're like, oh, no. The paper, first of all, is like, oh, that's just another one in the YZ plane. What are you doing? And our minds are like, oh, no, that one is still in this XYZ space. It's really hard for us to picture that one going in another direction. And but it's perpendicular to the previous three. It's hard to see, first of all, because we don't really think in 4D. We think in 3D, spatially, right? Once we get 4 spatial dimensions, we have to start looking at things in slices. We have to start looking at things in pieces. Another way we could think about things, another way that we want to think, I don't know if we want to. Want is kind of strong, it's kind of weird. Another way that we can think about these things, think about extending into dimensions. If I just draw a point, that's 0-dimensional, right? I can make this 1-dimensional by stretching it along an axis. And creating a length. Right, so, stretching it along 1 dimension, I've created length. If I take that length, and stretch it into another direction that I haven't used before, we can create a 2-dimensional area. So I'll take this 1-dimensional length, and I'll just take this and pull it straight down. Area is equal to length times width after all. I've got length, let's throw in some width. Now I just take that little 2-dimensional area and I pull it in a direction that I haven't already pulled it. I'm going to pull it forward out of the paper and create a 3-dimensional volume. So I'm going to grab this and pull it out of the paper and create a 3-dimensional volume. It's hard to see. Let me do this at an angle. And now we're still okay. Even though this is a 2-dimensional representation of a 3-dimensional object, we can still fool ourselves into thinking this is a 3-dimensional volume. Can everybody picture this 3-dimensional volume, this little rectangular block? Can you picture that as a block? Is it a block? No, it's a 2-dimensional drawing. But you can imagine that blue square being pulled forward out of the paper. Or do you imagine the blue square being pushed back into the paper? I don't know. Now, if I want to take this 3-dimensional volume and turn it into a 4-dimensional volume, hypervolume, I just need to take this 3-dimensional thing and yank it along a direction that we haven't used before. And we look at that and we think, well, shit. I've already squashed out 1 dimension by flattening out my representation, but I'm using your imagination. But now I've got to take this to, I don't know, somewhere else in another dimension, another direction. And things get weird. How bad could it be? Let's try. Let's take our 3-dimensional thing. For some reason, I'm putting it farther away. See, I'm drawing it smaller. Oh, I'm going to have a whole other dimension. So I'm going to push it farther away. See how it's smaller? What we're going to do is we're going to grab each of these vertices. And just like before, I'm going to grab each of those vertices and I'm just going to drag them into a dimension that I haven't used. Start with that 1 point, drag it into a dimension I haven't used. Take these 2 vertices, drag them down into a dimension I haven't used. Take these 2 points, drag them down here. And then take these 4 points and then drag them into this 3rd dimension. Now I just got to take these 8 points and pull them into a 4th dimension. So this is the new one that showed up. These are the 2 new ones that showed up. Then these 4 are the new ones that showed up. So these are my 8 vertices in the dimension that I haven't used before. And they just all got dragged out there. I see some of you are trying to copy this. That's funny because it's about to get so messy, you're going to give up halfway through. So we just need to connect the corresponding vertices. No problem, right? This is my original one up here. Here's where I stretched it out. Exactly. This is not actually a tesseract, but a tesseract is a version of this kind of thing. Now, this just looks like a mess because it's hard to picture in our 4D mind where that 4th one is. And we've squashed 2 dimensions out of this, right? This is like not just a 2-dimensional projection of a 3-dimensional object. It's a 2-dimensional projection of a 4-dimensional object. So we don't know what it looked like at the beginning, and we're not able to kind of put that together with this picture. But that's all we did. We just take each of the vertices, drag them into a dimension that we haven't used before, and then that's how it created a thing. Let's draw a 5-dimensional hypercube. That's not. Because I've only got 2 dimensions to work with, but all we would do is grab these 16 vertices, yank them into a 5th dimension that we haven't used yet, and then just connect all this stuff. Yeah. It would just end up being a bunch of lines, seemingly random around the page. It's hard because you got to know where to put that second block so that the lines seem distinct. Most of the time when I do this, they all just kind of like end up being on top of each other. And you miss out on some of the messages. Any questions? How's everybody okay? This is why we need stuff like equations. We need to be able to represent 4-dimensional objects that we can't picture. Remember in your algebra class, they're always like, "Oh, draw a picture." And then we get into things and like get into linear algebra. It's like, "Oh, here is a 6-dimensional space." And you look back at your algebra teacher, it's like, "Oh, you said draw a picture. I got 6 dimensions." I'm not saying that wasn't useful to draw a picture. It's always useful to draw a picture. But at a certain point, we need to look at an equation and know what that is. I need to look at ax plus by plus cz plus dw equals e and think, that's a linear function in R4. No problem. Got this. It's like a flat 3-dimensional surface in R, or flat , thing in R4. Line, plane, box. So that's what would happen if we're in R4 and we say everything perpendicular to this. There would be a three-dimensional thing sitting in R4 that would be flat. We describe it as flat. How's everybody okay? I don't know if this will help on chapter 12 homework, but one of the things you'll find out very quickly being in my class, it almost never helps on the chapter 12 homework. This is because I have a two-prong approach to making you learn math. Because I just work on the assumption that I'm forcing you to learn math. And I have a two-prong approach. Number one, I ask you to struggle with some homework, which are questions that I didn't come up with. Number two, I ask you to struggle with the questions that I come up with. So there's like the standard representation of things, and then there's my representation of things. Does that make sense? I'm not the Cliff Notes or the Spark Notes. They're Spark Notes now, right? Anybody remember Cliff Notes? Spark Notes. I'm not the Spark. I'm not the audio book. I'm the Spark Notes. You're supposed to point out the stuff around the stuff that you're reading. Does that make sense? You need to know how I think about things. That'll answer your questions like, oh, why don't you just do homework problems in class? My answer to that is like, oh, that's your job to do the homework problem. I've already done the problem. Not easy. All right, so start thinking about stuff in space. Think about your surfaces in pieces. Look for distinctive pieces of an equation. If you see an x squared plus y squared, if x squared plus y squared equals something, what does that make you think of? Circles, right? If you see like cosines and sines, what does that make you think of? I'm glad no one said sinusoid and somebody just like started doing this. Like, oh, perfect. That is the sinusoid dance. If you see an e to the x, what does that make you think of? Exponential, right? It's real steep. If you see dividing by 0, what that make you think of? Not just like this, but like steep, like vertical, goes vertical. Exponential doesn't go vertical, it just gets real steep. Divided by 0 makes things go real steep, like vertical. And undefined at a point. Those are the kinds of things you want to think about. Think in pieces. Take your weird picture, drop it back, look at it in pieces. That's how we envision this. We imagine this in all these different slices. Imagine in slices. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.